Welcome back. Sorry, I'm just gonna get my camera oriented here. Didn't get that set up before I started. Oh, right there we are. So we have talked about multiple resistors and multiple capacitors in a circuit, and that was all prelude to discussing, or at least starting to discuss, real circuits, if I can call it that. I'm going to now give you the basic ideas of analyzing my first approach to a real circuit. This is the examples I'm going to do are still terribly primitive compared to any real circuit that you might find in any non-trivial device. But the principles, the physics principles that I'm going to show you here apply to all circuits, regardless of how complicated they are. I'm only going to be dealing with, at least in this lecture, I'm only going to be dealing with multiple resistors in a circuit. Obviously, any real circuit is going to have lots and lots of different kinds of electronic components, but the physics, as I say, underlying all of them will be identical. So, and since I want you to focus on the physics rather than well, the physics class is not an electrical engineering class, so I'm going to give you the principles, and then you can apply those principles to any circuit, no matter how complex, in any of your future courses. So to that end, let me do this first of all. Let me just give you the first non-trivial circuit that I want to talk about, and it looks like this. So we will have, let's start out here, we'll have a battery, and resistance there. And then we have here some other source of resistance, and then another one, why not? And then maybe another battery here, like that, and some more resistance, and then over here, yet another device, and that's probably enough. Okay, and let's label these things. So this thing here, I will label V1, first battery, and this resistor here, I'm going to give it the symbol lowercase r1 for reasons I'll explain in a moment. This one will be capital R1, capital R2 here. This will be V2, little r2, and then finally R3. Okay, so what's going on here? Well, first of all, each one of these resistive devices is, you can imagine, is some sort of electronic device that you want to operate by running a current through it. So you have a toaster and a vacuum cleaner and a television and whatever else you may have. And those are the three big resistors. They're, anyway, the capital R symbols for those. As for the little r's here, the fact is that when a current runs through a battery, batteries also have some resistance to current flow. And so it's a common practice to label the so-called internal resistance of a battery with a lowercase r to distinguish it from the resistance offered by devices that you're trying to run with your circuit. So conceptually, we can link the potential, sorry, I didn't mean to do that, link the potential and the resistance of the battery together, but as a matter of calculation and analyzing the circuit, it doesn't really make any difference that this internal resistance is part of the battery. as you'll see. Okay, the question that we're going to answer is, given this particular arrangement of resistors and multiple resistors, multiple batteries, or multiple sources of electric potential anyway, what current flows in this circuit? Okay, so let's start out just by thinking about it. So we talk about a current flowing, and so if you imagined a charge Q here, and let's think about what happens to it. Let's consider what happens to this charge as it makes its way around the circuit. Okay, let's think about the physics here. The charge, remember, we're assuming conventional currents here, so this is going to be a positively charged charge carrier. So it goes from a low potential to a high potential, so it gains this much potential, which we're calling V1. So crossing the battery here, it gains potential. Then it crosses this resistor here, or the source of resistance, the internal resistance of the battery, and there it loses some potential through via Ohm's law. And then, but it makes it through, and then our charge makes it to the resistor R1, where it loses some more potential, then to R2, where it loses yet more potential, and then to the other battery, the V2. But here, notice that the charge is going from a high potential to a low potential, and so it's again losing charge. Now, it may seem odd that a charge going through a battery is going to lose potential, but the way these two batteries are wired together, if you look at it, I have the positive end of this battery electrically connected to the positive end of this battery, and so the result is that I've put the two batteries head to head, which of course normally to use them you'd put them head to tail, top to bottom. I put them top to top, and so it looks as if this circuit, at least one of its functions, is to recharge one of these batteries, whichever one is larger. In any case, so the charge, our little charge here, falls from a high potential V2 down to zero potential for V2, and so it's a loss of potential there. Yet another loss of potential across this internal resistance, another loss of potential across R3, and then finally it returns to its starting point, and that's the end of all the changes of potential. The key issue here, though, is that once the charge has returned to here, the amount of potential energy it has is the same when it returns to this point as it was when it left this point. There's a couple of ways to think about that. As it goes, it gains some potential, and then it loses. So evidently, well, let me say this first. But the thing is that remember that potential and potential energy is a function of position, and a change of potential is when a particle moves, when a charge moves from one point in space to another point in space, the change of potential that the change of potential energy that occurs to that charge is independent of the path that the charge took in going from its starting point to its ending point. And by extension, and this next thing is what's actually happening here, if a charge moves from one point in space to another point, if the charge starts somewhere, moves around a path, and returns to its starting point, okay, that's a closed path. And our closed path integral, E dot dl, remember, for an electrostatic field, which is certainly what we have here, each of these two batteries supplies an electric field that is constant in time. For an electrostatic field, this curl is 0, but this is, of course, the negative of the change of potential, right? And so basically, V is equal to that. So what I'm saying here then is that the net change of potential is, as you traverse this circuit, go from a point on the circuit, traverse the entire circuit, and return to that same starting point, that net change of potential in that trip around the circuit is 0. So what that means as a practical matter is that if you add together this increase of potential plus all of these drops of potential, that sum must be equal to 0. In short, all of these changes of potential end up canceling. Okay, and that, although I hope you recognize that that's just an application of the general concept of conservation of energy, the application of this concept to a circuit was first pointed out by, I believe, Austrian physicists, could have been German. Anyway, actually, I think about it, anyway, it doesn't matter. I'm trying to remember the nationality of the guy who first pointed this out. His name was Kirchhoff. And this is Kirchoffs' first loop rule, suggesting other loop rules, and that's correct. So I believe his name was Gustav Kirchhoff. And so this statement was, as I say, his application of the concept of conservation of energy to an electric circuit. The net change of potential around a closed circuit path must be 0. All right. And that statement then allows us to actually calculate what I said I wanted to calculate, how much current actually flows in the circuit. Because what we'll do is we will write down this statement in mathematical form. We'll traverse the circuit in our imagination, write down the change of potential as the charge crosses each element, add all those changes together, demand that that sum be equal to 0, and then solve for the current. That's a good introduction. Let's do that in the next recording.